Bismillahirrahmanirrahim. Hello, my dear students. I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. I am Azmat Ali. Our discussion is continue on chapter number 8, Primitive Roots and Indices. In last lectures, we discussed the concept of order of an integer, modulo n, primitive roots, Theorem 8.1 to 8.3, some important examples. In today's lecture, we will discuss a very important theorem that is a core topic of this chapter, and we will use this theorem in our next lecture. This is Theorem 8.4. This is important, very important, according to your exam. This theorem says let GCD of A and N is 1. Mean to say they are relatively prime. We know if the GCD of two integers is 1, they are called relatively prime or also called coprime. And let A1, A2 up to so on A phi n be the positive integers less than n and relatively prime to n. These are some integers which are denoted here A1, A2 up to so on A phi n. Phi n, you know, this is called Euler-Tauschant function. This is called Euler-Tauschant function. And this function actually gives the number of all those positive integers which are less than n and relatively prime to n. So these are some integers A1, A2 up to so on A phi n which are relatively prime to n. If A is a primitive root of n, this is important. If A is a primitive root of n, then the power of A square, A cube up to so on A raised to power phi n. These all power are congruent to modulo n to A1, A2 up to so on A phi n in a sum order. What does this theorem says actually? This theorem says if A is a primitive root modulo n, then its powers generates all integers coprime to n. Actually, this is the statement of this theorem. If A is one of the primitive root of n, then it must be that all power of A square, A cube, up to so on A raised to power phi n, because the last power will be A phi n. At this power, its answer will be congruent to 1 modulo n, according to the definition of its order. So its all power will generate all integers coprime to n, and the integers which are coprime to n, we have denoted them by A1, A2, A3 up to so on A phi n. But it is not necessary that the first power is coprime to A1, the second power is coprime to A2. That's why he explicitly says they are congruent modulo n in some order. So it is possible that the A square is congruent to A5, A cube is congruent to A7, etc. Firstly, we elaborate this theorem with the help of a very simple example. Then we will move towards its general proof. Okay. Take n is equal to 7. Then phi of 7 equal to 6. Phi of 7 mean the number positive integers which are less than or equal to 7 and coprime to n, coprime to 7. These are 6. Because 7 is a prime here, and we know the value of phi at any prime p is equal to p minus 1. So when p is 7, this is equal to 6. So the set of all positive integers less than or equal to 7, which are co-prime to 7, and this set is also called reduced residue system modulo 7, which is abbreviated by RRS. So the integers which are less than or equal to 7 and co-prime to 7 are simply the first 6 integers. You can easily verify that each of the integer is co-prime to 7. Co-prime mean its GCD should be equal to 1. So GCD of 1 and 7 is 1. GCD of 2 and 7 is also equal to 1. Up to so on, GCD of 6 and 7 is also equal to 1. So these all integers are co-prime to n. These are the 6 integers. They can be counted by phi of 7. So let the first integer a1 is 1, a2 is 2, a3 is 3, a6 is 6. Next we choose a primitive root of 7. In our previous lectures, I proved that 3 is a primitive root of 7. In this example, here we will again show 3 is a primitive root of 7. Next we compute powers of 3 modulo 7. The first power 3 raised to power 1 is simply equal to 3, congruent to 3. 3 square. 3 square is equal to 9, and 9 is greater than your modulo 7. So you will divide 9 by 7. Your answer is 2. So 3 square is congruent to 2. 3 cube is 27, and 27 is greater than your modulo 7. So we divide 27 by 7. This will become 7 3 is 21. Your remainder is 6. So 3 raised to power 3 is congruent to 6 here. Similarly, you can calculate other power. 3 raised to power 4 is congruent to 4. 3 raised to power 5 is congruent to 5. 3 raised to power 6 is congruent to 1. So the last power is congruent to 1 shows the order of 3 is equal to 6. And 6 is actually phi of 7. What is the definition of order of an integer modulo n? The definition of order of an integer modulo n says, suppose a is relatively prime to n, that is GCD of an is 1, then a is called primitive root of n if its order is phi n. Mean to say a raised to power phi n is congruent to 1 modulo n. So if the order of an integer is phi n, then it is called primitive root. I was discussing what is the definition of order. A least positive integer k is called order if a raised to power k is congruent to 1. This is the definition of order of an integer. Now if its order is phi of n, then it is called the primitive root. So here 3 is the primitive root. Now you can see here what is the answer of the powers of this primitive root. You can see here answers are 1, 2, 3, 4, 5, 6. So the powers of 3 generates this set, and this set is actually same as above. We have discussed a1, a2, a3 up to so on a6. This is the same set that can be generated by the power of 3, and 3 is the primitive root. What will happen if a number is not a primitive root? Still it will generate all power of still its power will generate all of the integer? The answer is no. For example, if you take here 2 from this set, you can observe that the first power is 2 raised to power 1. This is equal to congruent to 2 modulo 7. its second power is 2 square, which is equal to 4, which is still less than 7. So we will not divide. We cannot divide here. 2 raised to power 3, this is equal to 8. And 8 is greater than 7. So now we can divide 8 by 7. This is equal to 7. 1 is 7, remainder is 1. So 2 raised to power 3 is congruent to 1 modulo 7. You can see here at third power, answer is congruent to 1. This shows that order of 2 is 3. Order of 2 at modulo 7 is equal to 3, which is not equal to phi of 7. So this shows that 2 is not a primitive root. Now if when 2 is not a primitive root, so you can check here what are the answers of power of 2. The answers are 1, 2, 4. So these are the only 3 numbers, and here in the set there are 6 numbers. So you can conclude that if an integer is not a prime, not a primitive root, then it will not generate all of the integers which are relatively prime to n. Suppose if someone take the next power, 2 raised to power 4. The 2 raised to power 4 is 16. When you divide 16 by 7, your remainder will be 2 here. So after power 3, the next power will repeat these numbers 2, 4, 1. For example, if you take 2 raised to power 5, 2 raised to power 5 means 32. When you divide 32 by 7, this will give 7 4s are 28, and the remainder is 4 here. So it will repeat these same numbers here. So now I hope you have a clear understanding what does this theorem says by this example. From this example, you can observe some of the important facts that we will use in the following in the proof of the theorem. Even 2 is not a primitive root, but the set that 2 generates 1, 2, 4. This set is a subset of this set, and so this is the relatively prime to 7 also. Further, you can observe that if 3 is relatively prime to 7, then all of these power, then all of the powers of 3 will also relatively prime to 7. For example, 3 raised to power 1, 3, 3 raised to power 2, that is 2, 3 raised to power 3, that is 6. These all numbers actually the same as this set. So that's why the powers of an integer which is already relatively prime to n, its power will also relatively prime to n. So now we move towards the general proof of this theorem. I have written because a is relatively prime to n, then all power of a will also relatively prime to n. This line you can observe from the proof from the previous example. Hence each a raised to power k is congruent modulo n to some one of the ai. This line also can be verified simply by the power of 3. What was the power of 3? 3 raised to power 1 was 3. 3 raised to power 2 was 9. And the congruent after dividing by 7, 3, 9, remainder is 2. 3 raised to power 3 was 27, which after dividing by 6 gives the remainder 6. So from these, and you can calculate all other power also. So from these powers, you can observe that these all powers, 3, 2, these all numbers are congruent modulo n to sum of ai. These are relatively prime, and these are congruent to n modulo to some one of the ai. For example, 3 raised to power 1 is congruent to 3, 3 raised to power 2 is congruent to 2, 3 raised to power 3 is congruent to 6, and my ai are 1, 2, 3, 4, 5, 6. So all of these power are congruent to one of the AI. One of the AI. The phi n numbers in this set. Clearly, this set has a phi n number because the first power is 1, second is 2, last number is phi of n. So clearly, the number of elements in this set are phi of n. Suppose the last power is a raised to power 10, then clearly in this set will be number are 10. So the phi of n numbers in the set are incongruent. This is important. So these numbers are incongruent by the corollary theorem 8.2. What was theorem 8.2 and its corollary? Its corollary says if a is any primitive root of an integer, then all of its powers will be incongruent. Mean to say, you have observed that the first power of 3 is 3. The second power of 3 is 9 and remainder is 2. The third power of 3 is 27, remainder is 6. These all powers are incongruent to each other. What is the definition of incongruency? We say that two numbers a and b are incongruent to each other, and it is denoted by this notation if n does not divide their difference. So you can observe that here all of the powers of 3 are congruent to itself, congruent to each other. For example, if you take 6 and other number is 3 and calculate their difference, 6 minus 3, you can observe that your 7, n that is 7 here, does not divide 6 minus 3. What is 6 minus 3? This is 3 and 7 does not divide 3. If you take the difference of these two numbers, 6 minus 2, then again you can observe that 7 cannot divide 6 minus 2 here. Similarly, other integers are 5, 1 and 4. If you take the difference of 4 and 5, 5 minus 4, again you can observe that 7 does not divide their difference. So these powers are incongruent to each other. So actually, why we can emphasize is on the definition of incongruency. When we say they are incongruent, it means they belong to different classes. For example, in above example, in which your number was 2 here. Okay, we take this. As here 3 raised to power 6 is congruent to 1, modulo 7. If you calculate 3 raised to power 7 by just multiply 3 on both sides, this becomes 3 raised to power 7 congruent to 3. This is 3 raised to power 7, this is congruent to 3. Now you can observe that after the power 6, the powers that you will evaluate which are greater than 6 will repeat these answers. So 3 raised to power 7 has equal to 3 here. So can you write these numbers 3 raised to power 1 and 3 raised to power 7 in a same set? No, because they have a same answer and the repetition is not allowed in the set here. So it means 3 raised to power 1 and 3 raised to power 7 belong to the same congruent class. So when you say they belong to different classes, mean to say they are incongruent, it means if in your set there are phi of n numbers and all of the numbers are incongruent, it means they are all different. So that is required to prove actually. So these all numbers are different, these all numbers are incongruent. So thus these power must represent not necessarily in order of appearance, must represent the integers a1, a2 up to a phi n. So what we have proved? We have proved that there are exactly five of n numbers. They are all different, and further, their power must represent one of the integers. So this is the concept of this theorem. I hope now you have a clear understanding of this theorem. Inshallah, in the next lecture, we will discuss a very important corollary that is related to this theorem. And actually, this corollary I have already been used in my previous lecture. This corollary says, if n has a primitive root, then the total primitive root for n are given by the formula phi of n. In next lecture, we will prove it. So if you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.